My guest again today is James Camus.
Tom, thanks for having me today. I'm going to talk about a ocean warming hotspot, which is abnormally hot in the northern part of the Pacific Ocean. The slide right here shows that warm spot. For reference, you can see North America, over on the left, Russia, and then the map shows the heat, the temperature, the outline of the warm blob, which is what the media and the scientists have nicknamed it, is there in black. You can see within inside that, there are some really dark red areas. That's the extremely high temperature. And then the medium red that's inside that outline is still above average. And then the yellow down below that is normal. So to me, after looking at a lot of the evidence, I'm certain that this warm blob was generated by heat flow from ocean floor geological features on the far left or western side of that, right by Russia. There are lots of warm blobs across the entire globe. So we'll go through this one, look at the geological details, and then after that, we'll take a look at some of the other analogs. The scientific community has been baffled by this warm blob and many others. They really don't have a, let's say, valid interpretation. What they have proposed is that it's the result of atmospheric conditions, specifically a pressure high over this. There's a lot of reasons why this just doesn't fit the evidence. So let's start by going to another slide here. Many people, of course, most people, I think, regard the ocean as something that's flat. You look at the surface, you're at the beach. This distance looks flat. When you see images of the Pacific Ocean, they're usually from space, and all you see is this big blue area. So it's understandable that people wouldn't think that there's a lot of topography to the bottom of the ocean floor. Well, nothing could be farther from the truth. This is an image of course, the whole globe, North America, Africa, South America, and then the water is taken away so that you can see the bottom of all the oceans. Now, what becomes very apparent is that there are very, very high mountains, bridges, all sorts of features on the ocean floor telling you that, of course, it's not flat. In fact, some of these mountains down here are taller than Mount Everest. So what we're going to do is we're going to look at the geology over there on the upper left of the slide here, which is our warm blob. So the mountains we saw there are demonstrated here in this kind of a schematic image. You can see on the left of that, there are some mountains. One of them is exuding lava. And then the Pacific Ocean over there. And then in the bottom of the Pacific Ocean, there's several layers of rock in yellow, brown. Now, I had made these just kind of flat. They're not. But for the convenience of explaining to you, I thought this would be a better way to do it. So you've heard of continental drift, I'm sure, where the continents move apart. Then later on, they get back together. So that's what's happening here, where the warm blob is beginning on the far western part of the diagram, or the map I just showed. The Pacific Ocean plate, or continent, is being collided with the Asian plate, or where the source of the warm blob is. When that happens, the layers of the Pacific Ocean plate get pushed down underneath the Asian plate, and they dive down. They dive down about 1,800 miles. So when those rock layers get down there, it's an extremely hot portion of Earth. And what happens is those rocks melt, and then they form this big blob of magma, sometimes called hot molten lava. You can see that at the bottom there, kind of a semicircle. And that has a lot of pressure to it. So what happens is that the lava breaks loose, goes upward, forms these black lines that are kind of squiggly black lines along the red lava, and those are major faults. So this lava makes its way up to the volcano, fuels it, it erupts, then part of the lava also gets along the flanks of one of these volcanoes right by the ocean. And then most importantly for this discussion, some of the lava exudes out into the bottom of the ocean, where it acts to warm things, like the warm blob. So let's talk a little bit about the broad general geology of where the warm blob is. This time I've got the Pacific Ocean in blue. I haven't shown the mountain ranges, but what I've shown is this outline of the Pacific Ocean with these red dots. What those red dots represent are earthquakes. And the warm blob is snug up against that in the northern part. And this particular feature with the red dots is called the Pacific Ring of Fire. It's one of the most active geological features on Earth. As an example, 90% of all earthquakes that happen every year happen around the Ring of Fire, and 75% of the volcanic eruptions happen there. So there's a lot going on. Now let's take a look. Oh, we did that. We took a look at the cross-section. Let's move on. So this is a close-up of an area in and around the bottom of the Pacific Ocean where the blob is. This particular one is just a little south in a trench or deep valley called the Mariana Trench. This extremely deep valley is about 7 miles deep. It's one of the deepest parts of the entire ocean. And then the center and the left part of this diagram shows some areas where you can see little teeny cone-shaped features like where it says geysers. Those are actually geysers that are emitting heat up into the ocean. And if you look around this screen, for instance, maybe to the left side of it, you can see all sorts of these things. And then when you also look at this image where the volcanoes are, that's a string of kind of underwater islands there. So there's a lot of geological features. Now, here's the really interesting part. This image is taken by high-resolution instruments during a project called the GEBCO project. It started in 2017. A bunch of countries and entities put together a lot of money, and they wanted to map the bottom of the ocean in far resolution. Now, of course, you would think, hey, when we've already mapped the ocean, turns out that's not true. We just really didn't see things. This is just an area of where they've done a lot of high-tech, high-resolution mapping. To date, the GEBCO project has covered about 27% of the ocean floor. Using the numbers of geysers and volcanoes that are present in this type of image, they've had to greatly upgrade their notion of how many geological features are on the surface, or on the floor of the ocean, and how many there are active. To give you an example, used to be that they thought there were around 50,000 or so geysers on the bottom of the ocean floor. Now, based on what they have, the estimates vary, but the average is about 500,000 geysers, and could be as many as 750,000. The same thing is true with the volcanoes, lots more than they had thought of. So this emphasizes the fact that, hey, the geology on the ocean floor may be emitting more heat than we thought. This is a perfect example of how things have changed in addition to the mapping of the topography of the ocean floor. This is an image from space of a volcanic eruption in 2022 called Hungatunga. Now, Hungatunga was located along the Pacific Ring of Fire, and it absolutely changed how we think of ocean floor volcanic activity, things emitted from it, how it affects the atmosphere, how it affects climate. And there's some quotes over here on the right that I thought I'd go through. Let's start with the top one. It says that the understanding of how this volcanic eruption affected things has really changed our thinking. The next one, submarine volcanism has overlooked global climate studies because there is typically not much atmospheric sulfur dioxide released. However, they have found out since that quote that there are huge amounts of sulfur, very low amounts of sulfur. So it kind of confirms that previous one. There's not sulfur dioxide emitted from them. Well, why is this important? It's important because the method they use for identifying volcanic eruptions on land from space is seeing this this mineral, sulfur, in the atmosphere, in the ash. Now, this doesn't come out of the volcanoes in the ocean floor, so they really have no way of identifying them. So this is a big step forward. Maybe volcanism in the ocean is changing our climate far more than we think. Next thing we're going to do is take a look at the source area, the two source areas of the warm blob. Again, on the left side, that's that temperature map. And I've put there the source area. That's over by Japan and an area in Russia called the Kamchatka Peninsula. On the right is the Pacific Ring of Fire and Japan. So first we'll take a look at the geology of Japan area. On the left, you can see there's Japan, Russia, and China in the gray. And then those wider areas are really the exposure of the ocean taken away and the geology beneath it. So what's important here is those black lines you see on the west side of Japan are major faults, actually just about the same size as the one we looked at when we saw the Pacific Ocean rock layers diving underneath the Asian area. So that's interesting. There's a lot of faults in there. Also on the bottom there, they've mapped these red areas, which are older lava flows. They're still considered fairly recent. And so that gives us an idea that there's been a lot going in the near past in the Japan area. On the right side is one of these geysers that we talked about in our maps. You can see that these things are just amazing. This particular one is about 100 feet wide, and many of them are about 500 feet tall. You can see that fluid coming out of there. That's really hot fluid. It has a few pieces of rock debris in it, makes a darker color. And the temperature of these things is absolutely amazing. They're 750 degrees Fahrenheit to sometimes 1,000 degrees Fahrenheit. So if you have hundreds and thousands of these in the Japan Sea to the east of it, that could add a lot of heat. Now, over on the east side of Japan, you'll see that dark blue lines. That's the trench. That's the Japan Trench. And that particular one is about 5 miles deep. And it joins down, like we talked about. The faults go down to hot molten lava, and they're emitting that there out into the ocean. Now let's talk a little bit about the Japan land volcanism. On the left side, you can see Japan, and those little triangles there are volcanoes. Japan has about 160 volcanoes, which is a lot in a really small area. About 90 of those are really active. So we're talking about warming the ocean. So why would we be talking about land volcanoes? Certainly you would think, hey, they really don't have much to do with warming the water. We did talk about before how the lava from the volcanoes spills down into the ocean. There is that one thing that most people don't consider as you look at that upper right-hand slide is that the ocean, the islands extend far down into the ocean. And because the lava comes up alongside them, it heats that areas, and that emits heat into the ocean as well. So it's not just the island and the lava, it's the flanks that extends into the ocean. On the bottom right is an example of an eruption that occurred in 2025. This is an indication of just how active some of the land volcanoes have been on Japan. And that, of course, reflects on how active the seafloor features are around Japan. So here's a really broad summary of what's been going on in Japan activity area. Recall that the temperature or warm blob we looked at is at its peak in 2025. So preceding that warm blob image, in 2023, we had an unprecedented marine heat wave, enormous ocean floor volcanic eruption. 24 experienced a lot of seismic activity. Now that's really saying something because Japan is one of the most seismically / earthquake active areas in the world. So say it has an uptick, that's pretty significant. Then many of the things down here in 2025, a lot of ocean floor volcanic activity. large volcanic eruptions, extremely high magnitude eruption in 12/9/25. I think we have that specific earthquake on another map later. Continued high number of earthquakes, and the faults have been extremely active. Now we're going to switch to that area I talked about in the Pacific Ring of Fire map, Kamchatka. This is the Kamchatka Peninsula on the left. That's an outline of it. The light blue areas around it are the ocean. The leftern part of this slide shows a lot of little dots, red, circles, green. Those are all geothermal activity on the surface of the Kamchatka Peninsula. It is amazing. This thing, excuse the pun, is on fire. A lot going on here. And that's an indication that some of the volcanoes there are extending into the ocean. Excuse me. On the upper right is something that happened in 2024. The Kamchatka Peninsula became extremely active. At one point, there were 6 volcanoes erupting at one time, which is very unusual. There are about, 90 land volcanoes on the Kamchatka, which are not shown on the left screen. One of the quotes from this amazing activity in 2025 below, one of the largest earthquakes recorded in modern history has seemingly set off a cluster of volcanoes in Russia, with 6 separate volcanoes near the Kamchatka Peninsula. Now, my interpretation of the earthquakes setting off the volcanoes, a lot of geologists like myself strongly believe that the magma, the lava moves up, causing the earthquakes and then fueling the volcanoes. Second quote down there, shaking the magma, which is the hot lava, can alter its movement, and that's the case. There's a lot of magma movement, lava movement, altering the Kamchatka Peninsula. So a review of the Kamchatka geological activity. In 2025, there was a large earthquake. Hey, let me go back here. There it is right there on the right slide, that red dot. Let me give you an idea of 8.8. That is one of the largest earthquakes to happen in modern history. I think it's in the top 10. So it really indicates that there's a lot going on in the volcanic activity there. Go back to this, multiple high-intensity shocks, volcanoes, a couple of quotes here, more volcanic activity than normal, vast geothermal resources, numerous volcanoes and hydrothermal vents becoming active. I thought this was one of the most interesting ones. This surge described by scientists as a rare parade of volcanic eruptions. Now we're going to talk about some of the characteristics of the warm blob. Here's that temperature map again. You can see the source area. And then this white line, which starts at the source area, moves out and then bifurcates towards North America, is a representation of one of the major currents in the northern part of the Pacific Ocean. So this is kind of important because that current takes ocean seawater and moves it from the source area across. What you see here in this image again is that the source area has a lot of really dark red high temperature. And then high temperature spreads out, kind of gets a little wider, creates the blob, and then eventually goes all the way over to the east and diffuses a little bit. So that's an indication that the geological source area is where the heat's coming from, not from a local area just off the coast of North America, which is what the current scientific community is representing. This is a different time showing that the warm blob, it's, you can see Russia, North America, and in between there is the warm blob, where these pulses of heat. So when you have pulses of heat come across an area like land or satellite view, what it means is it's probably volcanic eruption. That's what's happening in Hawaii. You get an eruption, things cool down, then you get another eruption and it moves across the ash and the atmospheric heating moves across Hawaii, and disappears. That's what's going on here. An interesting characteristic. Another one is the concise outline. So there's a very strong difference between the temperature and the border of between the warm blob and the ocean. As an example, if you look to the left of the warm blob, then go down a little bit and look at the black line, you'll see on the bottom of the black line, yellow, which means normal temperature. And just above it, you see a pretty strong change. For reference, the temperatures, the warm blob temperature, the really dark ones, are 4 degrees Fahrenheit above normal. Now, that might not seem a lot, but when you're changing the temperature of an area, the warm blob area that is approximately 1,500 miles across and about 300 or so miles wide, it takes an immense amount of power to change that. To save that temperature and a concise boundary like that, it indicates it probably, well, let me say, it's not from atmospheric warming. I've built kind of a slideshow for you that's going to represent the warm blob building on the far west and the warm blob moving to the east. It's a little complex, but that's kind of how geological things form. So I'm going to go through this real quickly. So you want to watch the Japan area. I think you can see that in the Kamchatka Peninsula, way over on the west side. Okay, here we go. Already, okay, let me go back. This is April 2024. This is May 2024. You can see that the temperature has moved all the way across this area to North America. Certainly there's no way that can represent atmospheric warming, just too diverse. Then it settles down a bit. Then there's 2 heat pulses. Then it grows, you can see it there. And then finally, it becomes intense and moves all the way over to North America. This image is the ocean temperature on August 22nd, 2025. Another characteristic of the warm blob is that there are helium emissions. Japan there, and you can see this dark black outlines in the ocean. That's the Japan Trench and some of the other deep areas. And then the red outlines are higher plateaus where there are many geysers and volcanoes. Helium. So why is helium emission from the Japan Trench so important? Helium is the gas they use to confirm that there are volcanic eruptions. And so you take a measurement from space, you see helium, it says, hey, this is a volcanic eruption. So there's definitely some kind of volcanism going on in the ocean trench there. On the right is an image from space of the 2012 emission of helium from a seafloor volcano. This one is very counterintuitive. It's a little complicated, but it's another piece of evidence or characteristic of warm blobs. So there's a cool blob associated with it. So hold on. How can you have a warm blob and a cool blob? Well, let me see if I can kind of state it in general terms, and then we'll go into the specifics. So in the area west of the Kamchatka Peninsula, that dark blue area, that's the surface of the ocean there. Beneath it are layers of rocks, just huge accumulations of them as per recent research studies. So very, very thick layers. And those layers are unique. They have little holes in them, the rocks do. And those holes are filled with icy ice in the pores. And there's also a little methane in them. So when the hot blob starts to form, and things get the water gets a little warmer, it doesn't really melt these rocks at the bottom. There's so much heat that it kind of constrains them, covers them up. But as the heat from the warm blob slows, the coolness of this water makes its way up, the cool water makes its way up to the surface. On the upper right is an example of that. It's a cross-section, a slice again through the Kamchatka Peninsula. What I've shown down there is that blob of molten lava. You can see the rock beds slanted, going downward to the left, like we showed in the big broad geological cross-section. And there are fractures that come up from that lava, like the ones we showed in the big, broad cross-section. And they go through these rocks that have this ice and cool it and move it up there. On the bottom left is a close-up of one of these rocks. And the light-colored area is, yes, that's ice. Contains a lot of methane. If you don't mind, I'm going to just get off the subject a little bit because this is something that's very, very interesting to me. They have discovered in the last couple of years that there's a lot more of these cool rock, ice-bearing rock layers across all of the ocean. And they're considering that to maybe be a possibility they could warm them and release the methane that's in them and use it to help charge and drive a lot of our energy. It's interesting because we really haven't thought about that. And maybe this temperature cooling we see, like the La Nina in the La Nina, La Nina is occurs because there's some cool rock down there, and it's associated with the El Nino. So that's another piece of evidence, kind of twisted evidence, that the warm blob in the North Pacific Ocean is geological. Now we're going to take a look at the progression of the cool blob from the west coast or west area of the source area. And it will move. Oh, you can also see, just the top of the label where cool blob is, you can see a warm area. That's the development, late development or last legs of the warm blob. Now we're going to watch this cool blob progress to the east across the warm blob area. Here we go. Already look at that big change. That's 9/30/2010, 10/4/2010. So that again is a movement that can't be explained by changes in atmospheric temperature. And then finally, here's where it expands to practically nothing. You can still see the remnant of the warm blob there, kind of in the top central part of the temperature map. Now we're going to talk about some other warm blobs across the ocean. All these are going to show you that they're geological. First, we'll start with the Bering Sea, which is just above the warm blob, obviously. Then we'll switch over to the Washington coast there where it says Cascadia, and we'll look in an area there. It doesn't have a warm blob yet, but it's got a lot of geological information that indicates in the near future a warm blob may be forming. Then we'll switch down to El Nino, and the Hunga Tonga is right there. Okay. Bering Sea. To get you oriented, the gray areas are, again, the continents, Kamchatka, Russia on the upper left, North America on the right. This is, again, the temperature map. And the Bering Sea is kind of a subset of the Pacific Ocean. You can see that on the south or bottom of the warm blob, there's a string of a gray area. That's called the Aleutian Islands. They come off Alaska. That has about 100 active volcanoes on it. Some of those exist out into the ocean. These became very active in 2014 and 15, and they provided the heated fluid that moved north on currents up into the warm blob area. Of interest, much of that heat spilled over and was carried into the Arctic Ocean. You can see that. I've written an article about the fact that that heat has acted to melt a part of the Arctic sea ice, which has been characterized as done by humans or atmospheric. That's not correct. On the upper right, another one of these geological maps showing the Aleutian Islands deep trench there in the hatch blue, the island trend in the red. On the lower right-hand side here is an eruption in 2017 of an ocean floor volcano in the area of the warm blob. Again, giving you a little evidence, specific evidence, that that area was very warm and the volcano was very active in 2017. up till and before in 2015. Now we're going to shift to the Cascadia area, again located offshore from Washington and Oregon. There's a string of volcanoes here in the ocean floor that have erupted in the recent past. On the right slide there, you can see some of those ocean floor volcanoes in the red dots, and when they erupted, quite a few. That really thick brown lines are fault traces, and you can see there are strong angles there, right and left angles. That's because these particular faults here, where the ocean plate dives under the North American continent, have kind of fractured up in this angle. That has allowed the hot fluids to come up on those faults and activate the volcanoes. The Axial volcano is of special interest because it's become active. They've noticed from satellite images and other measuring techniques, including earthquakes, that the Axial volcano is close to erupting. They're predicting that it'll erupt in 2026. Along with this heightened activity along this ocean floor volcanic area, there's been heightened earthquake or seismic activity onshore. I don't know if you heard, but Mount Rainier, right outside of Seattle, has had 4,000 minor earthquakes. Now, I'm not trying to say there's an imminent danger here. I don't want to overstate that or get anybody believing, oh, there's a problem. No, but it has become more active. The old Mount St. Helens eruption, which you may remember, which has happened, I think, 30, 40 years ago, that has started to have a few little seismic activity. So when you combine this all together, the offshore area has become active, the onshore area has become active. So being able to see the Axial volcano getting going. Oh, I forgot one important thing. The Axial volcano was first noticed in 1985. Accidentally, they were able to see a lot of hot fluids at the surface. They investigated it as best they could, and the government of the United States decided to form a whole new entity, a whole new group called PMEL. Their task was to look for these types of unusual volcanoes all across the world in the oceans. About, I don't know, the last 10 years or so, they dropped that way they were looking at it and decided to just look at the environmental impacts instead of tracing more of these things. The Axial volcano, by the way, when it did erupt in 1985, warmed an area 16 miles wide by, what was it, 10,000 feet deep, so a huge area, 0.5 degrees Fahrenheit in 48 hours. That doesn't seem like much of a rise in temperature, but to do a volume of water from the bottom up to the top, 16 by 16 miles in 48 hours is absolutely amazing. Last one here, the warm blob analogs is El Nino. The temperature map here is from August 30th, 2023, and it gives you an idea that the warm blob temperature high and the El Nino temperature high really coincide with each other, kind of directly adjacent to each other. Both of these share a lot of characteristics. The source area, the white dots, so if I'm saying it's comparative, that El Nino is, well, then how do I know that El Nino is geological, kind of confirming that the warm blob is geological? Here's a few characteristics of El Nino. On the top there is the source area in that triangle. And this is a view from space of an ash cloud from a volcanic eruption. And you can see that that ash blob cones out the atmospheres. The current of the atmosphere makes it spread out. On the bottom here is the temperature map of an El Nino. From the source area, you can see that it expands out in a triangle. Looks just like volcanic ash, doesn't it? Another one is that there is helium being emitted from the source point of El Nino. You can see the top there. There's again the cone shape of El Nino. And the bottom is a map of helium using satellite to look at it. Source point, you can see that there's some helium there. and then the helium concentration fans out in the same cone shape in the exact same area as El Nino. So now let's look at a few of the analogs. Ah, I did that. Had my slides out. Whoop, there we go. Few of the analogs. There we go. I'm going to look at the upper right part of this image. The outline we're looking at is south of Greenland and east of North America off the coast of Europe. Over here, the way the warm blobs form over here is different, the basic geology. We talked about continental collision over in the warm blob. Here in this area, we're talking about continental drift. I'm sure you're aware of that. The continents move apart. Geologically, they spread apart. This is how that works. If you cut a big slide through the entire Earth and you look at all the various layers, down there in the lowest semicircle is the core, which is all sorts of heated molten lava. Then the next layer is the mantle, and that is extremely viscous, very loose, and it flows upward through the entire area and upward punches through the crust. Let's see if I can do this. Right there is the crust of the Earth. Now, not this whole thick thing, just that barely visible dark line. That gives you an idea of the perspective of actually how huge the volume of this magma or lava is that's coming up. So it comes up here, it pushes out and pushes out. When it comes up, it forces the continents this way and this way. That's what's forming the warm blobs in this area. Here's the first one. In 2010, the Gulf Stream current slowed down dramatically. It was characterized by the media and the scientists as a shutdown. It didn't actually shut down. So what is the the Gulf Stream current? This is a velocity map of the current that circulates around from North America up towards Greenland, goes down across Africa, down, and eventually makes its way back up along Cuba, into the Gulf of Mexico, and then northeast up towards Greenland. If you don't know much about the Gulf Stream current, this was used by the early explorers to go from Spain all the way down over to Cuba. Then when they're done, make their way back to Spain. So this one, stopping, is pretty amazing. On the bottom, there is a volcanic eruption, the E volcano on Iceland, and it was one of the largest volcanic eruptions in the history of Europe. It sent ash all across Europe and stopped air traffic for a long time. So this is an indication that there was a lot going on in 2010 in the warm blob area. Oh, I forgot to mention, let's go over there. This is that fault that comes up and distributes the lava, and you can see that the ocean is heated right where that comes up. And this part of the warm blob I didn't draw, but that yellow fault would go right through there. This is one that's same as kind of that warm blob we just showed. In 2023, the northern part of the Atlantic Ocean warmed up dramatically, just the northern part. You can see there that the southern part, where there's that yellow and another current flowing around, really hasn't gotten very warm. In fact, there's some blue, it's below normal. However, when you look at the northern part of the Atlantic Ocean, it has become very, very red. So that is pretty amazing, knowing that the Atlantic Ocean is the second largest ocean in the world. The graph on the right gives you an idea of how amazing this increase in temperature was. See if we can go through this. There's a lot of lines, thin lines of varying colors close together. That represents the temperature changes from 1981 to 2024 of all the data that they have in the northern Atlantic Ocean. So let's get down here. Each of these represents a 1 year all the way across the diagram. So in wintertime, all the temperatures of this are lower per year in the North Atlantic. Then in summertime, as you might imagine, the surface temperature of the Atlantic Ocean is higher, and all these fit together. Here's the amazing thing about the warm blob in North America in 2023 and 24. When you look at the temperature variance starting in May of 2023 to right here in September of 2024, the temperature has risen 2 degrees Fahrenheit in 4 months, the entire North American area. To do that again, pretty amazing. Something is going on geologically. Conclusion. There's a tremendous amount of evidence here that the warm blob is geological, and that a lot of the warm blobs across here, the globe, are geological. They're not to do with atmospheric warming. I think that maybe there's been a bit of bias here when geologists from NASA and NOAA look at this. I can't believe that they haven't at least looked at the geology of this to explain the warm blob, rather than just looking up at the atmosphere. I'm not trying to degrade them. I'm just saying, I don't know, this is kind of geology 101. So hopefully that's given a good amount of information to you about why I believe the warm blobs are generated by geological activity. Now I'll close it out there.
Okay, wonderful. That was very well presented. Appreciate it. How well known do you think this stuff is now? That do you think people are becoming aware of this theory?
Let's see. No. I really have read as many articles I can about this. There's been one research study that came out of a Chinese university stating that they believed it was an atmospheric thing. I haven't heard anything about people talking about the basic geology of the ocean.
Do you have any predictions about what's going to happen in 26? Can you tell at all, El Nino or La Nina wise?
Difficult.
Yeah.
They can't even predict it. But El Nino is, there is usually seismic earthquake activity about 6 months before El Nino starts to form. That's a difficult one because volcanoes turn on and off erratically, so predicting them is difficult. An example of how they can't predict them is that they make statements in the press. NOAA does, the National Oceanic and Atmospheric Administration, on when an El Nino will form, when it will be at its maximum. They only predict 6 months out. And for as long as I've examined this, I've been looking at these predictions since 2014. They're very rarely correct, even in a 6-month view. So the changes at the magnitude of the El Nino, when it'll come, they can't do a very good job there. Again, indicating, well, it's not atmospheric.
Can you steel man their hypothesis as to what causes an El Nino? Or
Yeah.
what are they using to make the prediction?
Sure. It's what's called the ENSO, E-N-S-O, and it has to do with currents. They've said that when the El Nino forms, that there's a change in the wind direction and the equatorial wind patterns. Instead of going from east to west, the big currents switch from west to east. They've also noticed that the currents in the ocean there change too. There's more deep currents coming up, deep currents going down on the South American side, which brings warm water closer, the heated water from the atmosphere closer to South America. It dives down and goes around. Well, I know someone, I won't say it who is a professional meteorologist, might be a relative of mine, who has a high degree from the University of Oklahoma. And he worked as a meteorologist for several companies, knows what he's doing. He and I have had some discussions about this. And he says, well, I think it fits the atmospheric thing. I took a lot of classes in it. But he said, oops, I almost said who he was. I think that you're onto something here, and it is possible. So I'm up against a lot of odds. But I think there's enough information that let's say I'm not correct. I'm not correct. At least I think there should be groups of people from NOAA and NASA that let the public know there's another possibility on El Nino and on the warm blobs. I'd like to see that put out there in the press. So that's how I've stole their ideas. And again, to kind of fit it in, I think we should get rid of here with the geology.
So generally, do we have detailed data on the speed and rate of change of speed of the plates moving around? Or do we know what's happening, and do we have any idea what will happen in terms of moving the plates around?
We do.
Yeah.
Typically, the plates move on average of about 2 inches per year in the active areas. So moving an entire continent from its surface area down to where it originates towards the bottom of the Earth layers, to move it 2 inches requires a lot of force. So they know that they moved on average about 2 inches. But here's an interesting example. Let's see if I can get up there. This warm area here, the one we talked about, the Gulf Stream warm, happened in 2010. Recently, this is related, I'll tell you how, there's been an enormous number of earthquakes right along here on the eastern part of the United States. There are areas where they've never had earthquakes before. Let me backtrack. They've very rarely had earthquakes in Maine, New Hampshire, New York City, all the way down to Massachusetts. Actually, they had some in Tennessee, and then across a few of them into the Midwest. So how does that relate to what we're talking about? That's because this area over here where that was that fault, that yellow fault that's spreading things out, has become extremely active, and it's pushing towards this. It's making some stress right across here, deep stress. So the rock layers there are pushed together. They have a lot of earthquakes. So they're pushed together by this movement of this plate. Is that totally my idea? No. It's actually been proposed by other people. I found out about it after I posted it on one of my articles. So that's it. Hey, before I forget, hope you don't mind, I wanted to try and show you my 2 books. The one on the left is The Geological Impacts of Climate. You can get that on Amazon. It talks about how geology affects all sorts of things: melting of ice in Antarctica, melting of sea ice in the Arctic, development of El Nino, a lot of other things in detail. Then I also have a book out called Geological Impacts on Antarctica. It goes into detail of, hey, what is really melting the glaciers in Antarctica? Turns out that a lot of the area underneath them is high rocks, maps of extreme temperature in those rocks by NASA, and also some volcanoes placed there by the University of Rhode Island, I think it was. Now, I've been in contact with these people, and they feel like, well, it's melting the ice, but maybe not as much as you think. I believe differently. So this book on the right will give you some detail about that.
So I do see a lot of people trying to look at the cycles of climate, all these different cycles. And do you think there's something here that as the Earth moves through space, that there's different poles of gravity, and that's pulling on these plates and causing maybe geological changes on Earth, that type of thing?
Definitely. Every 100,000 years, the Earth changes its orbit around the sun, becomes more elliptical. It changes the gravitational pull on the Earth. They're called Milankovitch cycles. So those are interesting. What happens is you start to put more strain on the gravity, which moves the continents. This has been researched by, I think it was Duke University, may get that wrong. They noticed that there was changes during Milankovitch cycles on the stress on the Earth. So that's one way to connect it to changes in astronomical forces.
Well, overall, do you think that there is also something to the cosmic ray theory and the winter gatekeeper theory, that all these things are happening all at once and interplaying to make it a super complicated thing to understand?
I'm sorry, I don't know much about that theory, so I can't,
Yeah, okay.
I can't answer that question.
And then I do hear quite a few people say that, oh, don't worry your pretty little head about geologic heat because it's such a small amount of heat that it doesn't add up to anything. You're not buying that?
Okay. Well, no. There's several examples in the past here. In, what was it, 1980, I think? There was an eruption in Indonesia called Pinatubo. It changed the temperature of Earth immediately, and it kept changing the temperature of the Earth for 4 years. Not a lot of value, but somewhere about 0.5 degrees Fahrenheit. But to change the atmosphere entirely for that many years is amazing. So if you were to have a series of those eruptions like that, you could dramatically change the temperature of the Earth. Geologically, we've seen that happen. Of course, the geological timescale is a little larger. I would mention another study by Cambridge University, and they said that the impact large geological eruptions have on Earth certainly is significant. But they noticed that when they looked at the sulfur dioxide, remember we talked about that, emissions from a lot of small, dormant or moderately active small volcanoes, which there are far more around the continents, they actually contribute to the sulfur presence in the atmosphere. And the sulfur presence changes the temperature. Now, I want to be sure to note that explicitly Cambridge didn't say those things are changing the climate. They just referenced some of the chemicals in the atmosphere. It's my interpretation that it changes the climate, but I think it's a pretty fair assessment.
So is there the work of any other people that you'd like to point out in this area that you think is particularly good or we should look at?
Let's see. Well, there's been a few people. You had us do a podcast not too long ago with three other scientists. Each of them felt, and they've done some investigation, that geological forces do have an impact on that. Maybe you can remind me of their names, but it was great to talk to them to see that they have similar ideas.
Yeah. The podcast we did, I will put the link in the show description, but it was Vitorito, it was you, it was Wis Yim, and it was Brian Catt, all on the same one.
Yeah, that's the one.
Ago.
Okay.
Yeah. Good. Let's see. Oh, and of course, you think that this mainstream idea that if you understand atmospheric chemistry, then you understand Earth's climate. That's the focus is not correct there necessarily, right?
Correct. Not necessarily.
Okay. All right. Any other points you want to make before we go ahead and finish this one off?
Yeah. Thanks again for having a podcast that allows people to present some alternative ideas, I think, that have some validity. And my hope is that your podcast will help make the scientists, the climatologists, a little more aware that there are some plausible alternative explanations to what is driving our climate and climate-related phenomenon.
All right, very good. And I should ask you, are you okay if I share your slides as a PDF on my Substack, or would you prefer I don't do that?
It's fine as long as you mention that I have checked the best of my ability and that the copyrights for all these slides are okay, either open access or public domain. So I don't want to think that I've stolen their slides and I'm going to be sued for a lot of money.
Okay. But actually, off the record, should I just not do it and then you don't have to worry about it?
No, go ahead.
Okay.
Yeah, I'm very rich. And I can go up against world lawyers. That's an attempted joke by geologists.
Fantastic. All right. Anything else before we sign off here?
No.
All right. Thanks a lot. That was really interesting. I appreciate your work, and I hope to have you on again, James Camus.
Yeah.